The objective of the limiting reactant lab was to identify the limiting reagent using a series of data collected on the chemical reaction of two aqueous solutions, 0.2 molar potassium hydroxide solution and 0.1 molar copper 2 sulfate solution, to create copper 2 hydroxide and potassium sulfate. This is a double displacement reaction, meaning that reactants exchange ions to produce new compounds. The limiting reagent is a reactant completely consumed in a chemical reaction, effectively restricting the amount of product created. For instance, given you have 12 burger patties and 10 buns, and you need 2 patties and 1 bun for a burger, you can only make 6 burgers. This being said, the patties are the limiting reactant because you cannot make any more burgers since you have used all your patties despite still having 4 buns left over. Using stoichiometry, the study of quantitative relationships between the proportions of reactants used in products formed by a chemical reaction, we're able to determine the limiting reagent. Stoichiometry is based on the law of conservation of mass, stating that matter cannot be created nor destroyed. However, in this lab, we used both qualitative and quantitative data to ascertain the limiting reagent.
Before beginning, we thoroughly cleaned our equipment with distilled water to ensure that our results were not skewed by existing compounds. Both reactants were transparent, but the copper 2 sulfate was blue in color, while the potassium hydroxide was colorless. Both were odorless. Using 2 burettes, we carefully dispensed 5 milliliters of copper 2 sulfate into 8 test tubes. Then dispensed 1 milliliter of potassium hydroxide into test tube number 1, 2 milliliters into test tube number 2, and so on. We also added water to the mixture to ensure that each test tube had a total of 13 milliliters of solution. We then used a stirring rod to completely incorporate the solution into each test tube. Placing them in the rack and allowing the products to settle for about 15 minutes, we used 2 beakers on either burette to catch any reactant that may have escaped out of it.
Continuing to stir the solutions to ensure proper results, we finally let the precipitate, a solid that emerges from a liquid solution within a chemical reaction, fully settle alongside the supernatant, the liquid above the precipitate. The precipitate was a light blue in all test tubes at first, but the longer it sat, the darker blue and more oxidized it became in test tubes 5 through 8, eventually becoming an almost black blue-green. Furthermore, the precipitate was initially suspended in the supernatant, having a chunky, jelly-like appearance until we further stirred it. Then, we measured the precipitate height in each test tube, observing that the height continuously increased in tubes 1 through 4 and plateauing in tubes 5 through 8.
In test tubes 1 through 4, the amount of precipitate increases as the amount of potassium hydroxide added increases as well, suggesting that it is the limiting reactant in these tubes only. Conversely, the amount of precipitate levels off in test tubes 5 through 8 because the limiting reactant, copper 2 sulfate, cannot create more product, as there is not enough of it to react with the increasing amounts of potassium hydroxide. In other words, the copper 2 sulfate is completely consumed in tubes 5 through 8, leaving potassium hydroxide in excess, and vice versa in tubes 1 through 4. Despite there being surplus potassium hydroxide to produce more precipitate or product, it cannot because the amount of copper 2 sulfate stays consistent, hence the lack of increasing precipitate height. The copper 2 sulfate is entirely consumed before more precipitate can be produced, ultimately resulting in a goal of precipitating height.
The height of our precipitate may have been slightly exaggerated, especially in test tubes 5 through 8 because it was not completely settled at the time of measurement. Our results may have been more accurate if we had waited longer to measure, perhaps overnight. However, our magnified results did not hinder our understanding of the key takeaway of the lab. Also, though we did stir throughout the lab, we did not mix it vigorously enough initially, which may have resulted in skewed precipitate heights.